So we continue with the properties of the convolution. So now we prove an important theorem, which is really the reason why the convolution is a very powerful tool in analysis. So let f be a continuous function with compact support on Rn, and let G Rn to R be locally integrable. Then f star G is continuous. If f is C infinity, so is f star G. Okay, so we saw that convolution can be defined for a continuous function with compact support and a locally integrable function. So there is no difficulty in making sense of that integral. So here is the very beautiful property. You take any continuous locally integrable function, convolve it with a continuous function with compact support, you produce a continuous function. And if you convolve it with a C infinity function, then you produce a C infinity function. And if you, in fact, we will see in the proof that if you convolve it with a CK function, the resultant function will also be CK. So you take any rough function and by convolution you make it smooth, a very smooth function. So this is called a smoothing operation. Okay. So let us prove. So we will show that f star G is continuous and that if f is differentiable, then d by dxi of f star G equals df by dxi star G. So you see, the derivative of this is, the derivative of f is again a continuous function with compact support, and then you can convolve it with G. So every time you want to differentiate, you put the derivative on f. So if f is C infinity, you can put any derivative on f. So by iterating this process, we can prove the entire theorem. So it is enough to prove these two facts. Okay. So first step, continuity. Okay. So let x belong to Rn and h in Rn, we can assume that mod h is less than or equal to 1 because we are going to take small increments, so there is no loss in generality. So mod of f star G at x plus h minus f star G at x is less than or equal to, by applying the definition of the convolution, this is mod of f of x plus h minus y minus f of x minus y mod gy dy. Okay. Now above integral needs to be taken only over a compact set Kx, which contains the supports of y going to f of x plus h minus y and y going to f of x minus y. So you can take, for instance, so example, you can take k of x equals x plus B closure 0 R, center 0 radius R, plus B closure 0 1, where B closure is the closed ball, center 0 radius R, where support of F, which is compact, is contained in some ball, therefore it is contained in B0R. So this H, this plus 1 is because to take care of the H, which is mod H less than or equal to 1. So this is a translation of a compact set, and sum of two compact sets is compact, we already saw. So if you translate it by a compact set, you still get a compact set. So it is enough to take this integral over Kx. Therefore you have mod. Now F is has compact support, F continuous with compact support implies uniformly continuous. Hence, there exists an eta greater than 0 such that mod H less than eta implies mod u minus v less than eta implies mod fu minus fv is less than epsilon. So now if you take, and without loss of generality, you can also take eta to be less than 1, the smaller the better. Okay, so therefore mod h less than eta implies you have mod f star g x plus h minus f star g of x is less than or equal to. So if you look at what is the difference here, this quantity is less than eta epsilon because mod h is less than eta and you have uniform continuity, and therefore you have less than integral over kx mod gy dy, and of course g is a locally integrable function, k is a compact set, so this is some fixed finite constant, and therefore you have since epsilon is arbitrary, so this implies f star g is continuous. Now differentiability. So let us assume that f1 is c1 and support f is compact. Okay, so let us again take x in Rn and h in Rn mod h less than or equal to 1, and let us take ei to be the standard basis 0 1 in the ith place and 0 elsewhere. Okay, so now in Rn of course. So then what is the definition of d by dxi of f star g at x? So this is equal to limit as h goes to 0 of f star g at x plus hei. So you have to take increment in the so h is not, so h is in R, sorry. So we are taking h is in R mod h less than or equal to 1, and then you are taking, so you are taking an increment in the direction of h, f star g minus f star g of x by h. So now again if you take kx is a compact set containing the support of y going to f of x minus y and y going to f of x plus hei minus y. So if it contains the supports of these two, then you have f star g of x plus hei minus f star g of x by h to be equal to 1 over h integral over kx of f plus f of x plus hei minus y minus f of x minus y gy dy, and that is equal to 1 over h I will remove, is equal to integral over kx. By the mean value theorem, this is equal to df by dxi of x minus y plus theta times hei gy dy, where 0 theta belongs to 0 1 and depends on x, y and h. So, we are applying the mean value theorem. Okay. Now, look at this integrand. So, df by dxi x minus y plus theta h ei gy in modulus is less than or equal to some m times mod gy on kx, because f is a C1 function, kx is a compact set, so the derivative is bounded. So, this is and this is integrable. And df by dxi x minus y plus theta hei gy converges pointwise to, as h goes to 0, to df by dxi at x minus y gy pointwise. Therefore, by the dominated convergence theorem, we get that df star g by dxi, which is the limit of that quotient which we are looking at, as equal to integral over kx, which I will now replace as the integral over Rn, and that is equal to df by dxi at x minus y gy dy, and this is nothing but df by dxi star g at x. And therefore, you see, for any derivative, now subsequent derivative, you just iterate this process. So, we can do, so remark, similar proof, in fact it is even easier if f is C infinity and G continuous with compact support. It does not matter where the support, one of them should be of compact support, that is okay. And therefore, and we can show, in fact, if f is suppose f is different, you can also show that d alpha, we can show if G is also differentiable, we can show that d alpha of f star G is equal to d alpha f star G or d alpha f star d alpha G and so on for appropriate alpha, where all these functions are defined. Okay, so you can partition, you can take, for instance, if this is in n equals 1, for instance, if f is in C3 and G is in C2, for instance, then f star G fifth derivative can be taken as the third derivative of f star the second derivative of g. For instance, you can partition and differentiate like this. So, you can differentiate in any number of ways. Okay. So, that is the beauty of this theorem, that namely you can by convolving a smooth function with a rough function, you produce a smooth function, and this has several important applications, and we will prove a lot of density theorems based on these things. Okay. So, the first application of this theorem, okay, rho epsilon family of modifiers. Then 1 f from Rn to R continuous implies rho epsilon star f converges to f as epsilon goes to 0, of course pointwise. 2 f Rn to R continuous with compact support, then rho epsilon star f converges to f uniformly. Okay. So, you see convolution with, and in this case rho epsilon star f belongs to d of Rn, because support of rho epsilon is compact, support of f is compact, and you saw that the support of rho epsilon star f is the sum of the two supports, with sum of two compact sets is compact, and consequently this belongs now a C infinity, because rho epsilon is C infinity, therefore rho epsilon star f is C infinity and it has compact support. So, if f is continuous with compact support, I can uniformly approximate it in Rn by a C infinity function with compact support. If f is continuous, then I can pointwise approximate it by means of a C infinity function. This function is C infinity, as you can see. Okay. So, this is the important application of the convolution. So, proof. So, let x belong to Rn. Okay. So, given eta positive, there exists delta positive such that mod y less than delta implies mod of f of x minus y minus fx is less than eta. Okay. So, now choose 0 less than epsilon less than delta, okay, and then you have rho epsilon star f at x minus f of x. What is this equal to? This is integral. First of all, I can enough to write this over mod y less than or equal to epsilon, because rho epsilon is of I am taking convolution. So, I am going to just take over the support of rho epsilon. So, that is enough to do that. So, I have f of x minus y, okay. Then here I am going to put just minus f of x. Now, in the second integral, f of x is a constant, it comes out. So, you get integral rho epsilon y, and we call that integral rho epsilon dy equal to 1. That is property of the modifiers, okay. So, we have that. So, now therefore, you have mod rho epsilon star f of x minus f of x is less than or equal to integral mod y less than or equal to epsilon mod f of x minus y minus f of x, and rho epsilon is non-negative. So, you can just put it out. Now, we saw that if epsilon is less than delta, then mod y is less than delta, and therefore, this is less than epsilon times integral rho epsilon dy, and that is equal to epsilon, okay, because the integral is equal to 1. Okay, sorry, that is less than eta, that is what we saw. Okay, and therefore, this proves the continuity. So, in the second step, so rho epsilon is C infinity with compact support and F continuous with compact support. So, rho epsilon star F is C infinity and support of rho epsilon of F is contained in support of rho epsilon plus support of F, and this is compact, and therefore rho epsilon star F belongs to D of Rn. And in step 1, the choice of delta is now independent of x, since F is uniformly continuous. F is continuous with compact support, therefore it is uniformly continuous, and therefore you have that this works. So, the convergence, therefore the convergence is uniform. So, corollary, so F continuous with compact support and then rho epsilon star F converges to F in LP of Rn for all 1 less than equal to P less than equal to infinity. So, proof P equals infinity already done, because we have proved uniform continuity, and that is exactly convergence in P equals infinity. So, let K be a compact set containing the supports of F and rho epsilon star F for all epsilon. Then we have uniform convergence on K implies convergence in LP K, and since everything is 0 outside K implies convergence in LP of Rn, because K contains all the supports. Now, why is it convergence in LP of K? Because you have uniform convergence, that is L infinity convergence, and K has compact support. So, its measure is finite, and consequently it is automatically convergent in LP as well. So, using this theorem, so we will now prove some important density theorems for LP spaces and C infinity functions with compact support, and we will see that next.